All right, this one's on catalysis, as you can see there. All right, so first of all, just a couple of definitions and things up front. So by definition, a catalyst is something that's not consumed or produced in a chemical reaction, but it somehow affects the rate of a chemical reaction. And mostly we're referring to catalysts when we're talking about things that speed up reactions. How they work, which won't become totally clear to you until I talk you through it, but they work by lowering the activation energy. Um, and they do so by providing, as it says there, an alternative reaction pathway between reactants and products. So they don't go through the normal mechanism for a reaction that lowers the activation energy and then that therefore speeds up the reaction. One really important point to make about catalysts is they don't actually affect the equilibrium constant of a reaction. They just speed it up the same in both directions. And of course, as I say there, that won't make much sense to you until you actually look at equilibria a little later on in this lecture. Okay, so the most important idea here is that catalysts actually lower the activation energy. When I say a bit, it might be by maybe a half or a third or something like that. You're normally not looking at catalysts lowering anything, the activation energy by any more than, say, an order of magnitude, something like that. But that actually has a profound effect on the reaction. And you can see that with this diagram here. So if I just grab a pen. So you remember this diagram before where you plot the number of molecules versus their kinetic energy here. And as I said to you, it's the actual area under the curve that tells you the total number of molecules that are present. And in the original curve I showed you, I drew the activation energy here. So this is the case where there's no catalyst, and what this means, of course, is the number of molecules that actually have an amount of kinetic energy that's equal to or greater than the activation energy is this number of molecules in here, in this area, under this part of the curve. Now, in the example I've given you here, more or less, this particular catalyst has actually lowered the activation energy from this value to this value, which is approximately half, right? So it hasn't actually changed the activation energy much. But what that means is because of the shape of the curve, it has a significant impact on the number of molecules now that actually have sufficient kinetic energy to react. And that's essentially what's happening with the catalyst, lowering the activation energy by some reasonably small amount, say a half or a third or something like that, but increasing the proportion of molecules that now have sufficient kinetic energy to overcome the energy of activation by a very, very large amount indeed. How that looks in a reaction energy diagram would be something like this. So what we've got here, of course, is we're plotting energy as a function of the extent of the reaction as before. And if we look at the normal case here, we've got some reactants here, and they're going to products here. And of course, starting off with this much energy, they're ending up with this much energy. So that's the difference there is the amount of energy that's released normally as heat, which is what that's showing there. And by the way, when reactions do that and they release heat, they're referred to as exothermic reactions. And if we go back here, you can see that for the uncatalyzed state, that's the sort of red-brown line there. Okay, the activation energy goes up. It's up here. So there's the transition state there. So that's the amount of activation energy. And then in the catalyzed reaction, again, it's about half, maybe little bit more than that, but it doesn't matter. So it's not, it's being lowered, but not by orders and orders of magnitude. But as I said before, that lowering there actually has a profound effect on the proportion of molecules with sufficient energy, kinetic energy, to overcome that activation energy. That means that overall reactions can speed up significantly. Now, another way you can do this, I basically did that in a very semi-quantitative way. Another way you can do it is to use the Arrhenius equation here. Now, you don't have to know this, but I'm just pointing out that this is basically telling you what the reaction rate is, and it's proportional to these values here. This value here is a constant. This is the temperature. So these two values are the same for this particular reaction, and what I'm showing you here is that the activation energy, we've changed it simply by halving it. That is going from 50 kilojoules, or 50,000 joules, to 25 kilojoules. So that the important point here to note is that you've just halved the activation energy. But when you plug those numbers into the equation here, the bottom line is you end up with these values, and you can see that they're significantly different. So we're looking here at this value here. We'll ignore the significans. We'll just look at the orders of magnitude here. At this particular reaction rate, so that's the uncatalyzed reaction, it's this value at about 10 to the minus 9. But for the catalyzed reaction, the value is 10 to the minus 5. In other words, we've had an increase there of around about 4 orders of magnitude. Now that's 10,000 times. And that's pretty typical for catalyzed reactions. So again, just to push home the point, where dropping the activation energy merely by a half, but the effect on the reaction rate is profound. It's 4 orders of magnitude. And again, that's coming back down to this idea in the area under the curve. Okay, so catalysts don't actually are not consumed, and they're not produced in reactions, but they do certainly make them go faster. And so this isn't a question of catalysts making things go and how far, but it's a case of if the reactions do go in a particular direction, can we make them go faster? And here's a classic example where we've got a car exhaust system here with a catalytic converter. And the bottom line is here that some of the exhaust gases are less than desirable. So for a car, one of the nastier exhaust gases is this one here, which is NO2. Nitrogen dioxide, and that's quite a nasty little brown gas. You actually produce some of that in experiment 1 in your prac, and it is caused because in your engine, of course, you suck in fuel, you burn that fuel, but in that process of burning that fuel, you're actually using air from the atmosphere. 80% of the atmosphere is basically nitrogen, so you're in effect burning nitrogen, and one of the products of that is NO2, which is this noxious gas here. Now, the good news is this stuff here is pretty unstable, but stable enough that if it's just spewed out the back end of the car, it'll end up in the atmosphere for quite some time. So the natural state of the reaction is for this to go essentially to completion, where all of this eventually gets converted to N2, which is in the atmosphere anyway, and oxygen, which is in the atmosphere anyway. So that's the good news. So if we could speed this reaction up somehow, so it just didn't go out the back end of the car and then this stuff break down naturally, but we could speed up the reaction here, that would be a good thing. So, and that's one of the jobs of a catalytic converter, is to do precisely that. One other noxious product in car exhausts is this stuff. This is carbon monoxide, so it's the incomplete oxidation of carbon. Carbon dioxide is nowhere near as nasty and toxic as this stuff. It sticks to hemoglobin and stops oxygen molecules binding to hemoglobin. And but it's reasonably unstable as well, and it will react with oxygen to form CO2, which is far more desirable. So that naturally occurs, but again, it doesn't occur fast enough, and often this stuff can get released into the atmosphere. So the way around that, of course, is to again pass the exhaust gases through a catalytic converter, and this stuff gets converted or it reacts, the carbon monoxide reacts with the oxygen much more quickly, and this reaction occurs before anything's emitted out of the back of the car. So that's a good thing. This final equation here is simply what you would want overall. Overall, you're taking hydrocarbons basically, normally around 8 carbons per molecule, burning them in oxygen, and really you only want coming out of your exhaust the obvious oxidation products, which are CO2 and water. So how do these catalytic converters work? Well, basically they work like this. Here's a diagram of carbon monoxide, right? And there's a diagram there with oxygen. Now, the interesting thing here is that the catalytic converter is basically some solid platinum here, and what it does is it tends to line these molecules up in the correct orientation so they can react. So you can see here we've got this carbon monoxide. This bond here is now semi-bond there and there. It's kind of half of a covalent bond each. That's why they're dotted lines there. Same with the oxygen. You get this kind of concertina effect going on here. And if you look back at your notes, you can see that if you want this to react, it's basically got to run with this oxygen combining with this carbon here. So it's getting them to actually combine up in the right way. If you look back in your notes, you'll see here there's no reaction, but it will actually promote this kind of arrangement between the oxygen and the carbon monoxide. There it is there. And that will actually speed up the reaction. So how does that look if we're looking at the transition state or activation energy diagram? Again, it would be something like this. We've got carbon monoxide and oxygen there. Right? It's going to end up very nicely forming CO2 there. Okay, plus some O, but that eventually gets used up as well. And the bottom line is there's our drop in the activation energy there due to this kind of mechanism going on. By the way, a lot of enzymes work this way, where they're basically taking molecules and putting them in the correct orientation to promote reactions. And again, it's doing that by lowering the activation energy. It's a different mechanism by which those reactants are actually reacting together. So speaking of enzymes, it's worthwhile noting that enzymes are these biological catalysts. They're made of proteins, and again, they work by getting the reactants to line up in the correct orientation, providing that alternative reaction pathway, lowering the activation energy, and of course then speeding up a reaction significantly. I put this in because a lot of this tissue damage here is because of bacteria that have actually produced enzymes that break down quite large body molecules, and naturally they will break down, but very, very slowly. And the bacteria are basically producing enzymes that are speeding up the breakdown of those large molecules that are comprising cells, etc., and then producing huge amounts of tissue damage. I put this in too because things like Sao biscuits, for example, you can store them for a very long time, And the moment you start eating them, they basically break down straight away into what were essentially large numbers of sugar units put together, and they break down with water and then produce sugar. And that happens because one, you're obviously supplying water to this, and the other thing that's happening is you're supplying enzymes, which then speed the reaction up again by thousands and thousands of times. Okay, I'll leave it there. That was the end of that particular section.